Hello, Organic Chemistry 2342. We're going to continue on with Chapter 20. This is Chapter 20, video number 2, Reactions of Amines. Okay, so the first thing we want to think about is how do we synthesize amines? And of course, we learned that we can use nitrogen and nitrogen-containing materials as nucleophiles when we talked about SN2 reactions. Unfortunately, it's very difficult to control because once you take ammonia and react it as a nucleophile with an alkyl halide, it produces a primary amine. The primary amine is also a nucleophile, so it can react with another equivalent alkyl halide to produce a secondary and then subsequently a tertiary amine, and even going all the way up to a quaternary ammonium salt. That being said, we're in equilibrium between having primary, secondary, tertiary, and quaternary ammonium salts on this, so it's very difficult to stop it in one place. Unless you want the quaternary ammonium salt and you use an excess of your alkyl halide, you have a difficult time just stopping at something like a primary amine. So we have to have alternative syntheses to get to primary, secondary, and tertiary amines. And the first synthesis of that is called the Gabriel synthesis. In this case, we're using an ammonia equivalent to create the primary amine and then go ahead and reduce it back down to our usable primary amine. So in the Gabriel synthesis here, what we're going to use is we're going to use basically this ammonia analog right here as a thalidomide right here. So this is phthalic acids that's been reacted with ammonia to make this thalidomide right here. And we're going to use a base to deprotonate the thalidomide hydrogen, giving us nitrogen as the nucleophile. We can then undergo an SN2 reaction to generate this intermediate species here. Then by either hydrolyzing this off with base or acid, we can or using hydrazine to actually reduce it down and get it off, we will generate the protonated primary amine, and then by basifying, we can get to our free amine synthesis. So notice that can only happen once because we only have the one nucleophile on the one alkyl halide. The other two groups of the nitrogen are blocked and are not released until we actually liberate it from the imide functionality. Okay, another way to do this is to actually start with an amide. And if we start with a primary amide, we can actually use bromine and hydroxide, and there's the mechanisms in the book here. But what we're doing is we're taking an amide and we're decarbonylating it and transferring the nitrogen to the R group of the amide here. Notice in the net result here, we are going to lose this carbonyl from the system, but the main chain forms the transfers over to the nitrogen here to give us our primary amide right here, plus a few of the decomposition products. Again, we don't really need to know the mechanism here. The key here is that we are doing only primary amides will work, and we are losing one carbon in that amide chain. So we want to make sure that we get our starting materials and products correct. Another rearrangement we have that actually also loses that carbonyl compound is what we call the Curtis rearrangement. And in the Curtis rearrangement, what we do is we take an acid chloride and react it with this sodium azide right here. And again, we don't want to use a lot of this. We want to keep these in solution because they tend to be explosive when they're heated. And what we'll do is we'll displace the chloride ion using the sodium azide to give us this acyl azide compound right here. And then what it's going to do is with heat, it rearranges to reform what's called an isocyanate. Notice the carbon is now bonded to the nitrogen and the CO is now bonded to the nitrogen as well. When we hydrolyze isocyanates, we get primary amines and CO2. And so we can just add water to the end of the reaction, decompose the isocyanate, and generate our primary amine. Notice this only generates primary amines because we're starting with sodium azide. There are no R groups on the azide when we begin. Therefore, it only generates the primary amines. Okay, another way using that azide ion to create these things is we can actually just take the azide ion and displace a halide on an alkyl halide as well. And in this case, again, we get a primary amine because we displace the halide and then we actually reduce down that alkyl azide using either a dissolving metal reaction with sodium metal and alcohol or lithium aluminum hydride. It adds hydrogen across the double bond and extrudes out nitrogen gas. So N2 gas is also liberated from this reaction here. So this is great if we have an alkyl halide and we know we want to make our primary amine from an alkyl halide, but instead of using just amine as our nucleophile, we use an azide ion as our nucleophile, and then we follow it up with a reduction to get that primary amine. We can also get our secondary, use our SN2 reaction, but if we want to add a carbon to the system, we can use sodium cyanide as our agent here. In this case here, we have our carbon is our nucleophile here that can come in and do our displacement on our bromide. Again, we're adding a single carbon to the chain here, and we have this cyanide at the end where we're going to hydrogenate that triple bond either with palladium on carbon or with lithium aluminum hydride to generate our primary amine with an additional carbon in the chain. So we can do it by using the azide system where we can lose a carbon by the acyl azide system. We can keep the same number of carbons by using the azide ion on an alkyl halide, or we can add a carbon by adding sodium cyanide to the system, displacing it and then reducing it down. So you have three different synthetic strategies where we lose a carbon, keep the same number of carbons, and add a carbon, all to create that primary amine. Okay, so once we go to aromatic systems, the most easily done system is to actually take our aromatic system, nitrate it, and then we take that nitro compound and reduce it down. We can either use catalytic hydrogenation with platinum or palladium, or what we can do is also dissolving metal reduction using iron or zinc with HCl. Note that other reducing agents like hydride, sodium borohydride do not reduce down aromatic nitro compounds. It works best with these iron metal or zinc metal with HCl to reduce it down to your aromatic amines, okay? Another way to get to a primary amine is actually to go through an oxime. And if you'll remember from our ketone chapter, an oxime is created when you take an amino hydroxy compound, react it with a carbonyl compound to create an intermediate, and then by reducing off that oxygen with either a sodium metal reducing agent, like we take sodium metal and ethanol or sodium metal and ethanol, we can actually reduce off that hydroxide and add hydrogen to the amine to also give us a primary amine. Okay. So we've also in previous chapters taken amines and added them to ketones, okay? The first step in that is to form a hemiacetal with a hydroxy amino compound, which then loses water and gives us our intermediate imine. Now, depending on which groups we have there, all these R's can be H's or C's. It depends on what you use in your starting material to generate that, but they can be all H's or C's depending on what you want. And then once we have this imine intermediate right here, we can reduce that down with either catalytic hydrogenation, or we can use a weakened version of sodium borohydride or lithium aluminum hydride. These are called the sodium borocyanate right here. Having that cyanide ion decreases the reactivity of the system, and it makes it less likely to over-reduce the system. Similarly, if we have the lithium borocyanide right here, it again weakens the system so it doesn't over-reduce the system. So what we can do is we can take any aldehyde or ketone. If we use ammonia, we will get a primary amine because the intermediate here is this, these two R groups are either R or they are H. And then this R group here is an H. And so when we have an H up here, we'll get the primary amine. If we start with a primary amine here, we'll end up with a secondary amine here because this R group is an R. And if we start with a tertiary amine, it doesn't fully form the amine, it forms an intermediate amine, which is then reduced and gives us the tertiary amine. So it's really easy to go from an aldehyde or ketone to a primary, secondary, or tertiary amine, depending on which amine you are using. And they are very selective. It all depends on what your amine you're starting with, determines what your final product is. We don't have any over-alkylation of the system as in with the SN2 of alkyl halides. Okay. So another way to do it is going from amides right here. And again, this is a very selective reaction. If you start with a primary amide, you end up with a primary amine. If you start with a secondary amide, you end with a secondary amine. If you start with a tertiary amide, you end with a tertiary amine. And you can use the same reagent for all of these right here. And notice you do not lose any carbons like in the Curtis rearrangement or the other rearrangements. We end up with the exact number of carbons we had in our chain here. What we're doing is we're adding hydrogen across this carbonyl bond here to give us our primary, secondary, or tertiary amine. So our carbonyl is the only thing that's being reduced. The amine and the alkyl chain are staying intact. Okay, so now that we have the idea that we can do these conversions here and we know that they act as bases, they can be bases with anything from very strong acids like HCl, or they can even react with carboxylic acids to deprotonate them. Remember when we did the reaction with acid anhydride and an amine, we had to have two equivalents of that acid of the amine because of the carboxylic acid salt that was liberated was deprotonated by the amine. So one equivalent got consumed to make the salt and one equivalent got consumed to make the amide. So we have the acidity of the system is the basicity of the amine is high enough to deprotonate both strong acids as well as carboxylic acids in most cases, especially if they're aliphatic. Okay, so how can we use this other type of acid-base reactions to our advantage? Well, one way we can do that is we can turn an amine into a much better leaving group. And we do this by reacting amines with what we call nitrous acid. Okay, unfortunately, nitrous acid is not very stable, so you actually have to create it in situ by taking sodium nitrite and reacting with a strong acid like HCl to create nitrous acid. So when we create nitrous acid, what it does is it reacts with amine and then removes water to generate what we call a diazonium salt. This diazonium salt looks very much like nitrogen. Remember, nitrogen gas is N triple bond N. Okay, so that makes it a really good leaving group. So by generating this diazonium salt in situ, we can displace it with any nucleophile and it will liberate nitrogen gas plus some kind of salt, giving us a substitution on a benzene ring. This is one of our few nucleophilic substitution reactions we have on a benzene ring. Okay. And the next video is some more reactions on amines.